In the last module, we looked at a very important concept of Prandtl number, which is the ratio of momentum diffusivity to thermal diffusivity. Based on the value of Prandtl number, which is a property of the fluid, Prandtl number was nothing but PR is equal to nu over alpha, which translates to mu Cp over K for the fluid. Based on this, we could have three types of fluids where Prandtl number of the order 1, Prandtl number less than 1 and Prandtl number greater than 1. These different types of Prandtl number, different values of Prandtl number gave rise to three different situations where the hydrodynamic boundary layer and the thermal boundary layer are of the same thickness. They grow at almost the same rate. That is where PR is the order of 1. So, in this, the velocity and temperature profiles would vary in this region only. Afterwards, this would be T infinity and this would be U infinity. This is PR of the order 1. PR less than 1 would be nu much less than alpha, and this would be this case. And this would have your velocity boundary layer growing only up to here and then virtually constant U infinity, thermal boundary layer growing all the way to a greater Y location. This is PR less than 1, and PR greater than 1 is the reverse case, where we would have delta of x, delta T of x. The velocity will change all the way up to this delta. Temperature would change only from y equal to 0 to y equal to delta T. Afterwards, it will be a constant value U infinity here. This is T infinity here. Okay. Based on this, we said the governing Navier-Stokes equation, we wrote only the Navier-Stokes equation and we wrote one term of the energy equation which we have not derived at all, but simplification of the Navier-Stokes equation becomes very good when we split the flow into these regions, and therefore, instead of solving the complete set of continuity x, y and z momentum equation in all its entirety in the whole flow field. Flow field means y equal to 0 to infinity and all the way along the length of the flat plate or whatever. So, instead of solving the entire set of equation, we will be able to solve certain simplified versions of the equations depending on where we are. This is going to help us reduce the computational time and effort and make the solution little bit more easy to reach. Okay. So, Prandtl number, again diffusivity of momentum to diffusivity of heat, and this classification is very useful because later on, where through scale analysis you will be shown a non-dimensionalization of the energy equation and scale analysis, you would be shown that Nusselt number is going to be of this form. This half or 1/3, the power of the Prandtl number. This is dictated by whether you have a thick thermal boundary layer or a thin thermal boundary layer. What are the fluids which have this? Liquid metals are examples where you have Prandtl number high thermal conductivities, right? So, liquid metals Prandtl number very much less than 1. Highly viscous fluids like oils etc., engine oil etc., PR much greater than 1. A very useful simplification sometimes when this inequality is this PR is much less than 1, you are talking of a case where this is your delta and this is your delta T. Okay. We can actually say that in such cases PR much less than 1, you can say U is approximately U infinity everywhere. What I showed you in the last module was where these were different, but they were not very small and very large compared to each other. They were If this was of a certain delta, this probably is 2 or 3 times that. Now we are talking of a situation where PR is much less than 1, in which case delta is much smaller compared to delta T, and you can say that the thermal boundary layer is doing this, hydrodynamic boundary layer is doing this throughout its u infinity. So, we can say u is equal to u infinity everywhere, and therefore, your rho Cp u infinity dt by dx, this is your energy equation left hand side term. Your momentum equation need not be solved because the flow field u is equal to u infinity everywhere would dictate v is approximately 0. So, you do not have to solve the momentum equation, you just have to solve the energy equation to get the temperature distribution. So, that is a big advantage. Instead of solving 3 Navier-Stokes, 1 energy and continuity equation, this approximation allows you to have u infinity, u is equal to u infinity approximately everywhere, thereby making the problem where you solve only the energy equation. So, it makes life a lot simpler for that. When you have Prandtl number greater than 1, the reverse helps us, that is, you have much greater than 1, this is your delta and this is say your delta T. You can say PR much greater than 1, you can say T is equal to T infinity everywhere. Therefore, no energy equation. So, you do not have to solve the energy equation because the temperature distribution is already known. No energy equation solution is necessary. You just have a hydrodynamics problem. So, continuity plus 3 momentum equation you have to solve in this case. So, the thermal problem is completely simplified. You do not have much to do with the energy equation. You just have to solve for u comma v in this part. This T is equal to T infinity everywhere will work. So, this kind of such simplification etc. will help us get an idea of how correlations are going to be looking like, and in your later on lecture you would see Nusselt number by scaling analysis would come out to be of the order of Re to the power of PR to the power half or 1/3, and this coefficient depends on PR less than 1 or PR greater than 1. The hydrodynamic boundary layer being thick or thin will decide the value of the correlation. What this tells us, see, this is not equal to, this means it is of the order of. So, Nusselt number is of the order of this one, means Reynolds to the half, PR to the power half or 1/3. Any correlation that is developed, please mark this, this is very important. Most of the time in our curriculum, we give a bunch of correlations, these are tabulated in textbooks etc., and these correlations are told to the students that you have to use this correlation under this situation and use this correlation under that situation, and many university examinations require students to memorize this correlation, and you will, it's a really unfortunate thing that you have to memorize formulae of which you don't know the basis also. Now, through this, which you will see, you will at least realize that for force convection, all your correlations are going to be functions of REPR. So, you have to emphasize to the student that if you are in a force convection problem, please note this, if you are in a force convection problem, Nusselt number will always be a function of RE and PR, whether it is internal flow, external flow, flow through a pipe, flow over a cylinder, flow over a flat plate, does not matter, whatever be the geometry, the Nusselt number is going to be a function of Reynolds and Prandtl only. This power half or 1/3 or whatever be the coefficient. So, typically we would write NUX is of the order RE to the power M PR to the power N. This X could be for a flat plate, it could be D for a flow over a cylinder. Values of M and N for flow over a flat plate you would get later on by scale analysis. I want to emphasize this a lot because Scale analysis, when we see, we will go into the details. It will tell you what terms are important and what contributes primarily. It's like, you have a bank account and you have a salary of say 50,000 rupees per month. You have interest from fixed deposit which is of the order of say 500 rupees a month, and you get a contribution from somebody every month for the tune of about say 500 rupees a month. In a given month, your income in the account is roughly 51,000. Bulk of the contribution is 50,000 from your salary. It doesn't mean the other two are zero. It means that the bulk of the contribution is from your salary. Those are small, very small compared to the salary. Suppose the interest from fixed deposits was of the order of 20,000 per month. Then 20,000 is not very small compared to 25 or compared to 50,000. Then you would not drop off, or you would not convey that, yeah, that is okay, I have some money coming from fixed deposit. That is 40% of your monthly income. So you would talk about that with a lot more importance. So the relative importance of these terms is gotten by the scale analysis, and what it tells us, these powers, whatever be the correlation anybody develops for flow over a flat plate, the powers have to be half and 1/2 or 1/3 for Prandtl number necessarily. What is different for each experiment is this coefficient C, which will be fitted or which will be obtained from experiments. So you develop a correlation for flow over a heated flat plate with some other conditions. M and N will come out to be half or 1/3. It cannot be some other power. Scaling analysis tells you that. Okay. The value of this coefficient can be obtained from experiment or from what we call a mathematical method called as similarity method, which we will see, or an integral method. But whatever we do, a correlation for Nusselt number, all of these would give you C2, this would give you C1, this would give you C. These alone would be different. The coefficient would be Re to the power half, Pr to the power half or 1/3 only. That would not change, and that is something which you have to emphasize to students, because they think that each correlation is a magic black box. It is not. Force convection, Nusselt number is function of Re and Pr, sacred. The power of Reynolds number for flow over flat plate is going to be half. That is also sacred, that is coming out from scaling analysis. The power of Pr is going to be either 1/2 or 1/3 for flow over a flat plate. That also comes from scale analysis, depending on whether we are dealing with Pr equal less than 1 or Pr greater than 1 situation. Which one is what, that you would see in the lecture. Integral method, we will show, we will talk about this method for a couple of lectures or a couple of modules. Similarity method we will do for flow over a flat plate Blachius solution. There you would get C1 and C2, these coefficients. Exact solution would be 5, which will be from similarity method. Integral method, depending on the complexity of the profile, paper and pen solution will give you something like 4.7 or something. So the most important thing that the students have to take from here is this: these correlations have not fallen from air. This is not magic, this is not a black box. These correlations have a lot of scientific thought which has gone into it. It has a lot of logic which has gone to it. Re, Pr are the only non-dimensional numbers for force convection. M and N are fixed based on geometry, and for the Prandtl number dependency, coefficient will vary according to the experiment that you are doing, according to the method of solution that you are doing. Integral method is an approximate method. Similarity method is a more exact method. Of course, nothing comes free. So similarity method is a very restrictive method, cannot be used for all kinds of flows. Integral method is more forgiving. You can use it for varying various kinds of flows, but the solution is approximate. This is something you have to convey to the students. Once this is done, we will go through this concept now of Lagrangian and Eulerian frame of reference. This also has been covered in fluid mechanics, so I would go through it a little fast. Definition of system and control volume. Lagrangian and Eulerian frame of reference. System in thermodynamics. We have seen this word many times. You have used this in fluid mechanics. Before that, you have used it in thermodynamics. System, you saw piston cylinder arrangement, 1 kg of air in a piston cylinder arrangement. That was a system. Closed system, open system, isolated system. Closed system is where mass is fixed. And for us in fluid mechanics and heat transfer, system refers always and almost always to a fixed mass entity. Control volume, on the other hand, refers to where the mass is going out or coming into the system or both. So, mass flow when it is there across the boundary. By our definition, this is called open system. We call this as a control volume. Control volume. Control volume. It is not controlled volume, it is just control volume. So, if this is my piston cylinder arrangement, this is my system M. Fixed mass. Control volume, flow through a pipe, mass coming in, mass going out. Mass coming in by some other means, doesn't matter. Whatever be the paths, we don't care about it. See, when you have hot water for bath, you would mix hot water stream with a cold water stream, and that is what comes out through the tap. So, you have two streams, one with m dot 1 T1, another with m dot 2 T2 temperature cold water, and what you get at the end is m dot 1 plus m dot 2 and some intermediate temperature T3, which is a comfortable temperature for you to have bath. How do you get this energy balance? MCP, m dot Cp T1 plus m dot 2 Cp T2 equal to m dot 2 plus m dot 1. M dot 3 is nothing but this value because mass is conserved. Cp T3, Cp will cancel. You get m dot 1 T1 plus m dot 2 T2 divided by m dot 1 plus m dot 2 is nothing but your T3. This we have seen in thermodynamics. So, this is my control volume, a region of interest through which mass can come in or mass can go out. Now, fixed mass entity system, mass allowed to come in, mass allowed to leave is called control volume. In fluid mechanics, there are two types of analysis possible. One is called Lagrangian and other is called Eulerian. Lagrangian and Eulerian are basically two different types of analysis, and in this we will, in one of this Lagrangian analysis, we will look at a system and keep following it. We will follow the system throughout and see what is happening to it. That means mass of air 1 kg, it can be heated, cooled, compressed, expanded, whatever, but we are concerned only with that 1 kg of mass. We are following it. Okay. So, it is like a bunch of students in the class, each one has a roll number. You put a tag on it, and this is done for tiger sensors and elephant sensors, etc. There is a chip which is embedded, and you track that particular tiger or the elephant, where it is going, how it is behaving, etc. So, when a particular species is tracked, in this case a tiger or an elephant, in thermodynamics and fluid mechanics, a particular chunk of fluid, that is called as the Lagrangian approach, tracking a particle or a system, where you have that in mind that this is what I am going to track. It could go, water could be converted to steam, steam could be converted to superheated steam, then condensed back to water, then cooled to ice, does not matter. You are tracking this 1 kg, m kg. That is Lagrangian. Extend this to fluid mechanics. This is passing through a pipe. it is going, taking a bend, it's going that way, going out into a larger pipe, its velocity decreases. Whatever happens, this is what you are tracking. In a class, each student comes from a different place. Once he is in the class, he is a roll number. If you want to track the behavior, it's like how a spy operates. You follow a particular person, see what he does throughout the day, when he gets up, whom he meets, what he does, what he eats, when he eats, where he eats, so on and so forth. That is Lagrangian approach. Eulerian approach is much nicer. It's less difficult. Imagine every fluid particle you are trying to track. What the amount of bookkeeping that you have to do. 1000 particles, each one behaving differently, each one is going to take care of everything differently. It's going to be extremely difficult to handle. If in a class, if there are 10 homeworks, 4 exams, 1 mid-semester exam, or 1 course project, 1 end semester exam, so on and so forth, if I track the marks of every student for all this, I am going to have a huge Excel spreadsheet with the database. Whereas if when I give the final total score out of 100, it's only one number per student. I don't care what the individual marks were. Each header was different, but the final score is 81 on 100, 72 on 100, 58 on 100. The complexity reduces. Eulerian approach is something like that, where I don't track individual effort, individual particles. I am sitting at a place and seeing what is happening in my region of interest. So if this is the pipe, I am sitting here and seeing what is the mass flow rate of the fluid going, what is the temperature of the fluid going, what is the internal energy, what is the entropy, everything. It's like a passenger sitting on the platform of a railway station and seeing what is happening. One train goes from left to right, 3 trains go from right to left, one is going at 20 km per hour, another one is going at 80 km per hour. Doesn't matter. What is happening in that field of interest, which is the station in which you are in, you are going to track that. These kind of studies are done typically for traffic at an intersection. 4-road intersection, you want to employ traffic signals, you do a survey. What is the traffic density going in the north-south direction versus east-west direction? In the morning it is from north to south, in the evening it's from south to north. East to west is pretty much constant throughout the day, so the signals have to be timed appropriately. So you would employ people to take a survey in 1 hour between 8:30 a.m. and 9:30 a.m. How many vehicles are going from north to south, so on and so forth. So Eulerian approach is basically looking at a fixed region of interest and seeing what is happening to that region. What is the mass flow, what is the energy flow, enthalpy, so on and so forth. This system analysis is your Lagrangian. Eulerian analysis is your control one. This is a fixed region in space through which mass is allowed to come and go. That analysis is called as Eulerian approach. When you are taking water for bath, it is not the same particle or molecule of water that you are tracking, right? You are not going to keep count of molecule A was what first came out, then what happened to the molecule after bath, it went into the drain. Are you going to track it? No. So you are tracking how much is the mass flow coming out of this pipe, m dot 1 plus m dot 2. So your tracking mechanism is now for a region versus Eulerian, which was for Lagrangian, it was for a particle. This is unique to fluid mechanics and therefore unique to heat transfer. Why? Because a fluid can accelerate, decelerate, etc. because of unbalanced shear stresses, and because of that a fluid may behave differently at different locations. Nozzle, for example, nozzle at steady state, you would have seen in thermodynamics, mass flow coming in is mass flow going out, but we all know V1 is much smaller than V2. Flow is accelerating, it is steady. Control volume analysis will tell me that dV by dt is greater than 0. We all know this from common sense, but mass flow rate is pretty much, because it is steady state, there is no change in the mass flow rate. It is as if a solid each particle of the solid will be at the same position with respect to the other particles. Whereas a fluid, on the other hand, if you see, if I look at this nozzle example, I take 1, 2, 3, 4, 5, 6, 7, 8, 9 particles at inlet. When they come out, these 9 are going to come out at the same time, because you are talking of steady flow. They are going to come out very, very close to each other, 5, 6, 7, 8, 9. The relative position between the particles has changed. That, though it is steady flow, m dot in equal to m dot out, we know that, but V in is not equal to V out. Acceleration not equal to 0. Who and what causes this? This is caused because the relative positions, the distances between the particles has changed because of change in position of the particle with respect to time. This is very, very important in fluid mechanics. Unlike solids where this doesn't exist, you have this particular fact that position of the fluid particle can change, which is the definition of the fluid. You have what is called as a fluid particle acceleration. Acceleration of a fluid particle, which is very different from acceleration of a solid. Acceleration of a solid, dv by dt equal to 0, no acceleration in case of solid. In case of fluid, this alone is not enough. Several other terms will come which represent the change in position of the fluid particle. That change in position coupled with change in velocity with respect to time would be the complete definition of the fluid particle acceleration. More on that in the next module. Thank you.